Hi guys, it's Physics Coach YouTube with Mr. Ward. The last time we were together and worked out problems, we did friction problems. Well, I'm not there right now, so let's work out some friction problems anyway. Okay, so here's our problem, the first problem. This one's a little tricky, but that's okay. We can figure it out. Let's read the problem and put down our given. So what we have here is a 2.35 kilogram mass on a 42-degree incline. The coefficient of static friction is 0.3 and the coefficient of kinetic friction is 0.25. When it's released, it slides downhill. Calculate its acceleration. How do we know it slides downhill? Because they told us it slides downhill. Later on, we're going to figure that out on our own. Okay, so first we have mass equals 2.35 kilograms. Theta, the angle of the hill, is 42 degrees. The static coefficient is 0.3 and the kinetic coefficient is 0.25. And the acceleration is unknown. We'll do that in meters per second squared. If you think about it, we don't really need the static coefficient because they said it breaks loose and slides on its own, so you can just get rid of that, get it out of the way. Okay, you might remember when we did inclined planes that we had some sine and cosine terms in there. So let's draw our little picture first of all, which would look like that. And remember what we had. We had the weight of the object. Here, I'm gonna do it over here. We had the weight of the object first, so that would be mg. And we have the normal force perpendicular to the hill, which is a little bit smaller than mg. And in this problem, so this would be Fn. And in this problem, we're going to have the frictional force. Since the object's sliding downhill, the frictional force has to be uphill. And of course, it has to be F kinetic in this situation. Okay, so that's nice. Since those are all real forces, we can just box this, and this will be our real forces free body diagram. And according to the problem, the acceleration would be that way. Okay, we need to simplify this or modify this diagram. And we know that we can take the Fn and the mg, and we can replace them when we have an inclined plane. We can replace those with mg sine theta. So there's our mg sine theta. And up the hill, we would have our F kinetic, and we'll make that shorter, of course, because if it's not shorter, the object won't accelerate. So this is going to be our modified diagram. And the acceleration is still going to be, of course, downhill. Okay, so this is a fairly simple problem in one way along the incline, but there's something else that's going to come up that's going to be a little tricky that we have to deal with. So first let's do Newton's second law in the down the hill direction. And looking at the problem at the modified diagram, what we see then would be, of course, mg sine theta minus fk equals ma. Well, we don't know what fk is, so we're going to have to replace that. So we get mg sine theta minus mu k fn equals ma. Now, here's where the tricky part comes in. Usually, we would continue along like this, mg sine theta minus mu k, and then we put in for Fn what? mg? No, because we're on an inclined plane. It's not going to be equal to mg. So what are we going to put in for that? If you remember back when we did this, the mg sine theta was the part that made it slide down the hill, and the normal force was mg cosine theta. We did this about 3 weeks ago, I believe, and that's equal to ma. Okay, so all we need to do now is cancel out the m's and just flip this problem around because it's already essentially solved for a, but let's put it with the unknown on the left, so a equals g sine theta minus mu k cosine, whoops, forgot somebody there, I forgot the g, so that'd be mu k g cosine theta. Okay, so all we have to do now is substitute, and as I mentioned before, I don't like to factor out the g because a lot of times it gets lost, so we'll just keep it like this. It's only a couple seconds longer to write the problem, so 9.8 meters per second squared times the sine of what was that, 42 degrees? Let me check that. 42 degrees. Oops, 42 degrees minus mu k, which was 0.25 times 9.8 meters per second squared times the cosine of 42 degrees. And then all we have to do now is do a little quick calculation. By the way, everybody should be taking notes on this, and everybody should have this calculator on, and everybody should type this problem in. So I'm going to do it. I'll give you a couple seconds, well, a little bit longer than that, to calculate it, and then I'll tell you the correct answer, and we'll see what happens then. Okay, I've got my answer. I'll give you another few seconds. Okay, so let's go ahead. The acceleration would be 4.74 meters per second squared. And we'll just write it as a magnitude because we know what the direction is. It's obviously downhill, so we'll just give the magnitude like so. Okay, so there it is. There's a few things in here that you might be a little rusty on. I think we've done the mg sine theta enough times that you're comfortable with that, but the Fn equaling mg cosine of theta, you don't have to derive that during a test or a quiz or a homework. You can remember it, but just make sure you remember it correctly. Okay, so that problem wasn't too bad. We'll call that problem number 1. Now we're going to go to a different problem in a little while. I mentioned earlier, how do we know that the thing slides down the hill? I said because they told us it did. Well, what if they don't tell us it slid downhill? What are we going to do then? Well, we'll figure that out in a few seconds. If you had any questions about that last problem, put a little question mark in your notes and make sure you ask somebody. Send me an email. Okay, let's take a look at problem number 2. This one's a little trickier. We did a problem like this way back when we first started friction, but this one's a little trickier than that. We're not going to put the givens and the unknowns down again. We already have those just to save a little time here. So what we have in this problem is another inclined plane, and let's draw it. So this would be the mg, and this would be the F normal, a little bit shorter than mg. And again, we have a frictional force uphill. The problem here, though, is will it slide? So what we're trying to find out here is this coefficient of static friction big enough to hold it on the hill? That's the only question we have to answer. Does it slide or does it not slide? So we have to take a look at F static here. So let's Mark this for our acceleration. Now what's the modified version of this problem, just like it was on the last one? Oh, by the way, this is not F static here, this is F static max that we're going to compare it to. Okay, so it won't break loose until the force is greater than F static max. So it's not just any old F static, it's F static max. So we know that down the hill, we don't know what's going to happen here, but let's just assume that one of these is bigger than the other. It doesn't really particularly matter because we don't know. So this would be mg sine theta. And then up the hill, or we can even make them equal and see if they are equal. This would be F static max. And this then is going to be our modified diagram with the acceleration in this direction. Okay, normally we would start now and write Newton's second law, but the problem is if we write it, we don't know what is going to happen here. We don't know if it's ma or 0. So what we're going to do is do this just a little bit differently. We're just going to look at the left-hand side. Look at the two terms on the left-hand side. So let's just assume that the downhill direction is positive. So what we would end up here would be mg sine theta. Let's just take it by itself and see what it looks like. And let's put the values in there. So what we would get would be 2.35 kilograms times 9.8 meters per second squared times the sine of, oh, this is not the right angle. This is the wrong angle. Let me go up to the problem itself here and put the correct angle up here. So that is, we'll use the magic pen here to point that out. Whoa, that's not what I wanted to do. Let's use the magic pen to mark that out. And of course the magic pen disappears. Okay, let's go back to regular. All right, so it's a 15-degree hill. Okay, so that's going to be the sine of 15 degrees. And let's see what that comes out to. So this says that the mg sine theta is equal to 2.35 times 9.8 times the sine of 15. Get your calculators, punch it in, and find out what you got in a minute. I got my answer. Give me a few seconds. Okay, it shouldn't take that long. So the value of this is 5.96 newtons. So this is one part of the net force. Now, let's look at the other part of the net force. That's going to be the F static max. Now remember, F static max is equal to mu static Fn, which of course is mu static mg cosine theta. So let's put that over here below the part we just did. So we're now going to say, let's calculate F static max. Wait, I won't. Yeah, we'll do that. Equals mu static Fn. And let's just say all of that is going to be equal to mu static mg cosine of theta. And now we put the numbers in and see what it actually is equal to. So this would be 0.3 times 2.35 kilograms times 9.8 meters per second squared. Uh-oh, ran out of room here. Okay, and then that would be times the cosine of 15 degrees. So, mu static, mg cosine of theta is equal to this. Get your calculators again, punch it in, and let's see what you get. Okay, I've got something. Okay, so what I got for this answer is 6.67. Okay, so these are our two answers. Underline in red. So the down the hill force, which is always there, is 5.96 newtons, and the frictional force trying to prevent that from happening can be, I forgot my units, can be as large as 6.67 newtons. Does it need to be that large? No. So what we're going to find out here is that F static in this problem, not F static max, F static would automatically have to be the same as the downhill force, 5.96 newtons. This 667 would only happen if we had a larger force down the hill, in fact 6.67 newtons. So what do we see here? The frictional force is able to match the downhill force, therefore the sum of the forces in this problem is going to be equal to 0 newtons. Therefore, the acceleration in this problem is 0 meters per second squared. Now that's kind of a tricky problem. If you didn't understand that, put a little question mark there. One of these days I'll be back there and we can talk about this thing a little bit more. And for now, just put a check if you understand it, put a question mark if you don't. Okay, let's take our third and final problem. Let's call that number 3. And we'll use the same information we had for the last problem, but what we're going to do this time is we're going to push it to get it started. And the assumption here is that the kinetic friction will be low enough that this thing will accelerate, and that happens to be what's going to occur, but we'll pretend we don't know that right now. Before we do the problem, let's just take a look at how we know it's going to accelerate. From the last problem, the down the hill component, the mg sine theta, was equal to, I forget, 5.96 newtons. And the uphill force, F static max, could be as large as, and that came out to be invisible, 6.67. Now that doesn't mean that because the F static max is 6.67, the downhill force is only 5.96. It wouldn't make sense for it to go uphill. And the reason for that is this is the maximum force, but what happens is the static friction turns out to be less than the force because all it has to do is match the 5.96 newtons. So in this problem, what we could do, we're not going to go through the whole thing in detail, we could do that same calculation of F static max, F static I should say. No, this one's going to be F kinetic. So in this problem we're going to look at F kinetic. So let's use green, so F kinetic then would be mu k m g cosine of theta. Mu k is only 0.25 times 2.35 kilograms times 9.8 meters per second squared times the cosine of 15 degrees. And Fk in this problem is equal to, that comes out to be 5.56 newtons. So I figured this out ahead of time so I would know if it actually did accelerate. And since the mg sine theta downhill component is bigger than the F kinetic uphill, it's going to accelerate downhill. Now let's take this problem, and I'm going to just draw a line under this part here, and I'm just going to erase this. In your notes, you could just drop down a line below that. Okay, so let's just start this problem from scratch, just as if we had never seen any of the other parts of the problem. So here is our free body diagram, mg. Fn perpendicular to the hill is smaller than mg, and F kinetic uphill and F normal here. This is a pretty easy problem. It's very much like the first one we did. So a modified version of this is going to look like so. We get the Fk uphill, and we get the mg sine theta downhill. And there it is. There's our modified diagram that we're going to take our equations off of. So net force equals ma. And the net force here would be mg sine theta minus Fk equals ma. Since we know it will accelerate, we'll expand that to mg sine theta minus mu k Fn equals ma. And one more time, mg sine theta minus mu k mg what? mg? Oh, we don't want mg in there. We're on an inclined plane, so we have to replace this with what? Not just mg, but mg cosine theta equals ma. Okay, get rid of the m's. Boom, boom. Solve for a equals g sine theta minus mu k g cosine theta, and we'll do the substitution. So 9.8 meters per second squared times the sine of 15 degrees minus 0.25 times 9.8 meters per second squared. There's the cosine of 15 degrees. So our acceleration is, get your calculators, punch it in. Give you a few seconds to calculate it while I do mine. Okay, got my answer. Give me a few more seconds. When you first see this answer, you might think something's wrong with it, but it isn't. Assuming you got this, it comes out to be 0.170 meters per second squared. Why is that so small? The reduction in the uphill force is fairly small, and remember, it wouldn't move at all before. Now we're making the uphill force a little bit smaller, so this gives you a little bit more downhill, which gives you a little bit of acceleration, this fairly small 0.170 meters per second squared. Okay, that's probably enough for today. If you have not finished problems 1 to 13 odd, you can work on those. I'm not sure how much time we got left, but we'll talk to you guys again soon. Bye.